I just hope I can use the blackboard as efficiently as some previous lecturers have. So we're going to be discussing supersymmetry in 4 dimensions. And although we will really be talking about n equals 2 supersymmetry, to begin with, we're not going to specialize to one value of the number of supersymmetries. We'll say some things in general, and we'll even do some things for n equals 1 supersymmetries. So I first write down the Susy algebra. And I will do that using 2-component spinors. So in 4 dimensions, there are 2 kinds of spinors, of positive chirality and of negative chirality. I indicate the negative chirality spinor by putting a dot on the index. Maybe I'll put a tilde on the guise of negative chirality just because it's easier to see instead of seeing that little tiny dot if you're halfway back. And then the supersymmetry algebra is that, well, we're going to consider the case of some unspecified number of supersymmetries. So we assume that the supercharges transform as n copies of a spinor. You might ask, by the way, why there are the same number of copies of both spinors. That's because in Lorentz signature, they're Hermitian adjoints of each other. I possibly would emphasize that by putting a bar instead of a tilde. We might occasionally be in Euclidean signature where that wouldn't be true. So I'm going to stick with tildes. So then the supersymmetry algebra tells us I believe that John Bagger used these matrices, sigma mu alpha alpha dot. Sigma mu, in a suitable basis, are the unit matrix and the Pauli sigma matrices for time and space. And then the rest of the standard supersymmetry algebra P mu are the energy momentum operators. The rest of the usual algebra is that Q alpha I with Q beta J is 0. And similarly for 2 Q's of the other kind. Now, before we go too much farther, you could ask why the supersymmetry algebra is what it is. Well, first of all, what are the bosonic symmetries that are possible? The usual bosonic symmetries are the Poincare group. It's possible to have a conformally invariant theory, which extends the conformal group to more space-time bosonic symmetries. It's also possible to have internal symmetries that simply commute with the Poincare or conformal group. A classic result of Coleman and Mandula shows that the S matrix is trivial. In other words, you have a free field theory if there are any bosonic symmetries other than those. So the moral of that story is that there's never a problem with internal symmetries which are Lorentz invariant. But bosonic symmetries that aren't Lorentz invariant generically cause troubles. So when we commute Q alpha with Q alpha dot, we can't get a Lorentz invariant because, in fact, we get a Lorentz vector. The tensor product of the 2 kinds of spinors makes a Lorentz vector. And the only Lorentz vector allowed by the Coleman-Mandula theorem is the energy momentum or possibly the special conformal transformations. We won't be discussing primarily conformally invariant theories in my lectures. So from our point of view, the only possibility here is the energy momentum tensor. Now, here it's a little bit more subtle, because when we commute 2 spinors of the same kind, we could either make a Lorentz scalar or a self-dual or anti-self-dual tensor. Now, okay, you could ask whether the self-dual or anti-self. So a slight further argument shows that the tensor can't be there in a theory that isn't conformally invariant. But the scalars can be, and later they will be. So although we will start with these lectures, this form of the algebra, we will add the scalars later on. They're known as central charges, and they'll be very important in the lectures. Now, the first thing which we want to do is to discuss irreducible representations of this algebra. And first we're going to look at states of positive mass. So when we discuss states of positive mass, of course, we could go to the rest frame. Where the energy momentum is in the time direction. And therefore, the algebra is that Q alpha with Q tilde, alpha dot, or beta dot, let's say. Well, remember that sigma 0 is the identity matrix. So what we get on the right-hand side is just a bunch of Kronecker deltas times the mass. And the others are 0. So what we have here is the algebra for 2n fermion creation and annihilation operators. Just think of the Q's as annihilation operators and the Q tildes as creation operators. Q with Q and Q tilde with Q tilde are 0. But Q with Q tilde is a constant. I mean, usually it would be 1. So we could divide by the square root of n. Divide the Q and Q tilde by the square root of m, and we would get the algebra of creation and annihilation operators as usually written. So, an irreducible representation has dimension 2 to the 2n. That's for the case of positive mass. Now, let's go to the case where the mass is 0. In that case, the best we can do to normalize it is to consider a particle moving in the z direction. And then the algebra looks like the following. See, I'm going to use the fact that sigma z is this explicit matrix. So 1 plus sigma z is this matrix. And 1 plus sigma z is what will appear because the right-hand side is sigma mu times p mu, but I've chosen p mu so that sigma mu p mu is just 1 plus sigma z times the energy. So our algebra is that Q alpha I with Q alpha dot j is equal to delta ij, that doesn't change, times twice the energy, times this matrix. And Q with Q and Q tilde with Q tilde are still 0. Well, the main change is that the unit matrix, whose eigenvalues are both 1, has been replaced by a matrix 1 whose eigenvalues are 0. Now I will use the fact that in Lorentz signature, Q tilde is the Hermitian adjoint of Q. So you see, Q tilde is Q bar. We're really going, or you might want to write it as Q dagger. It's the Hermitian adjoints. So if I set alpha and alpha dot equals 2, I find that Q2I anti-commuted with its adjoint is 0. No sum over I here. In other words, Q2I with its adjoints is 0. Now, in a unitary theory, I'm really worried that this thing is blocking the view of some of you. Okay, I think I'm not wise to do this. Sorry. I've reduced the solid angle a little bit, but we better not try to do more.
I'm worried it's attached.
Okay, I know it's attached. That's why I'm not trying to do more.
Oh, okay.
Like I said, we were lucky to reduce the solid angle without causing a mess here. So we have a Hermitian operator, we have an operator whose anti-commutator with its adjoint is 0. But on the other hand, the anti-commutator of anything with its adjoint is positive semi-definite. So the only way out, don't worry about this, it won't bother us too much. The only way out is that Q2 and Q2 tilde are 0 on these states. On m equals 0 states with this energy momentum. And so after we set half of the Q's to 0, we have the same picture, but there are just half as many of them. Instead of 2n, so this was for positive mass, but for 0 mass, we get n creation and annihilation operators. So in this case, an irreducible representation has dimension 2 to the n. That's an irreducible representation of supersymmetry. But as I'll explain, with CPT, sometimes 2 times 2 to the n. Now, as you'll see, this is an important result because unless n is rather small, 2 to the 2n is bigger than even 2 times 2 to the n. And as soon as 2 to the 2n is bigger than 2 times 2 to the n, funny things will happen. So we're going to look at some small values of n. So we'll start with n equals 1. And we'll start with the massless case. Now, a massless particle is in a representation of the Poincare group determined by its helicity, which is an integer or half integer that I'll call little j. So, well, I'll list the possible values of the helicity. So, -3, -5 halves, -2, and so on, and then we get up to positive numbers. And for n equals 1, there's one creation operator and one annihilation operator, and they are spinors which transform with angular momentum plus or minus a half around the z-axis. So our creation and annihilation operators raise and lower the helicity. So we get 2 states, and they differ in helicity by half a unit. So the representation looks something like this. That's an example. that would be part of a supermultiplet in supergravity, a pair of states of helicity -2 and -3/2. Now this is an easy example also, where CPT would force a doubling. CPT reverses the sign of the helicity. So if we do have -2 and -3/2, we also will have 3/2 and 2. Now, with a little thought, you'll see that for n equals 1, we actually never get a CPT self-conjugate spectrum with only 2 states. So for n equals 1 and m equals 0, we always need 4 states. Now, in these lectures, we won't be doing gravity, so we'll only be doing gauge theory. So we want the representations where, at least for the massless particles, the helicity is no bigger than 1. And there only are 2 such representations. I can draw a truncated version of the picture because we're only interested in the part where j runs from -1 to +1. So, well, there's the vector multiplet. It's called a vector multiplet because it contains a field of helicity plus and minus 1, in other words, a vector field. And there's what people call the chiral multiplet. That has its highest, well, what it's defined to be, let's say, is a massless supermultiplet that doesn't have vector fields. So the largest allowed helicity is a half. We could represent the superalgebra with helicity 0 and a half, but then CPT would tell us that we also need helicity minus a half, and then we need a second state of helicity 0. Now, I'm not going to completely work out the possible multiplets for positive mass. I think you heard some of it, or such things, in the first lecture this morning. Well, I'll just make a comment or two just for fun. If you look at this spectrum, first of all, it consists of 4 states, which was how many we needed for a massive multiplet. And in fact, this multiplet can get a mass in a completely supersymmetric fashion. This multiplet obviously can't get a mass by itself in a supersymmetric fashion because the vector would become a massive spin 1 particle, which would have a state of helicity 0, which is missing. So that's a phenomenon that's familiar without supersymmetry. For a massless vector to get a mass, it has to combine with a massless scalar that becomes its longitudinal part. And so we have a supersymmetric version of that. This guy can't get a mass by itself, but when you combine it with this guy, which can supply the longitudinal part of the vector, it can become massive. By the way, that then gives you an 8-dimensional representation, which, as I've explained, is not irreducible purely as a representation of supersymmetry. It is, however, irreducible as a representation of angular momentum plus supersymmetry. I won't prove that for you, and I didn't even give it in the homework exercises. But it is a good thing to make sure you understand. Okay, now we're going to move on to n equals 2 supersymmetry. And in these lectures, we really won't get higher than n equals 2. So we'll do n equals 2, but we'll do first the massless case. So, as we know, we've got 2 creation and 2 annihilation operators. So the basic multiplet looks something like this. It's got a lowest angular momentum, which I'll call minus j, a lowest helicity. Let's start with one state, whatever the lowest angular helicity is going to be. Then we've got 2 helicity raising operators. We had the two Qs and the two Q tildes, which one group of them raises helicity, one lowers helicity. So there was one state at helicity minus j. There will be two at helicity minus j plus f, and one at helicity minus j plus 1. So that gives an irreducible representation of supersymmetry, but we still need to worry about CPT. Now, for most values of minus j, it's obvious that we need to double the spectrum for CPT. Because, for example, if minus j is minus 1, CPT will tell us we need something of helicity plus 1, and that will give us a second multiplet. There's one funny case you can worry about if minus j is minus half. So I'll write that one in detail because it's important. Here are the values of j, and we have an irreducible supermultiplet with 1, 2, and 1. Which also, remember, we had the same spectrum for n equals 1 supersymmetry. For n equals 1, we started with, for massless case, two states, one boson and one fermion, differing in helicity by half. But CPT made us double the spectrum. And the doubled spectrum was exactly this. So you could ask yourself, since this is an irreducible representation of supersymmetry, is it possible to have an n equals 2 theory with a massless spectrum which is precisely what I've written? It represents the supersymmetry algebra, and it doesn't in a trivial way fail to be CPT invariant. But it fails in a more sophisticated way to be CPT invariant. CPT means that, I'll make a statement that has nothing to do with supersymmetry. CPT means, first of all, there's a notion of what it means for a quantum state to be real. The CPT invariant states are the ones which are real. And whatever is the algebra of observables, if we consider the algebra of all Hermitian operators in the theory, their representation in the quantum Hilbert space is a real representation. In other words, one that commutes with CPT. So in this case, so half of the Q's and Q tildes were 0 on these quantum states. Let's just look at the ones that weren't 0. So we had 2Q and 2Q tilde, which means 4 Hermitian operators. You can think of the Hermitian operators as being Q plus its adjoint and I times Q minus its adjoint, where there are two choices of Q. And these 4 operators generate a Clifford algebra. Then there will be no representations. If M is sufficiently large, the right-hand side is positive, and we learn nothing. And if M has a magic value that makes the right-hand side 0, we learn that in an irreducible representation, these two operators for the lambda that makes the right-hand side 0 are represented by 0. And then our representations become smaller. So to make the right-hand side as negative as possible, we pick lambda bar equals minus z over m. So lambda is minus z bar over m. And then with that choice, this becomes m times 1 minus z bar over m squared. So you see that the minimum value of m is the square root of z bar. If m is bigger than the absolute value of z, the irrep has 16 states, just as if z were 0. But if M equals the absolute value of Z, the E-rep, well, it has 4 states, or with CPT, 2 times 4, which is 8. So that's actually the answer, you see. Okay. Now we can better answer the question, given a single massless multiplet, if n equals 2, can it become massive if we change the coupling constants a little bit, preserving n equals 2 supersymmetry? The answer is that if it's going to become massive, the deformed theory has to have a central charge. And yes, it can become massive, but its mass will be the absolute value of its central charge. So its mass will be predictable from supersymmetry.
The right-hand side is larger than 0 at this point.
At which point?
It's equal to m. If we take lambda to be z bar over m, the right-hand side is equal to m. So it's not that.
What? I hope that isn't right.
Yeah, it's 2. Yeah, probably.
What? Lambda is minus z bar over m. It's actually, I might have said it wrong, but the minus signs are on the blackboard. So this is a plus, but these two become negative, and we get the formula I've written. Any other questions? Okay, now we're going to construct the most basic theory that actually has n equals 2 supersymmetry with gauge fields. Well, in a way, it's the most basic renormalizable theory with n equals 2 supersymmetry, other than a free theory. The reason is that there are renormalizable theories with hypermultiplets only, but they are free. There isn't any analog of a superpotential in a theory with vector multiplets hypermultiplets only that lets us have interactions. So if we want an interacting theory, we need vector multiplets. And then, in a sense, the most basic theory is the one that has vector multiplets only. So I've told you already, although I think it may have been erased, what the field content is. The field content is a vector, 2 fermions, and a complex scalar. And we're going to construct this theory in 3 ways, although I think we will probably only manage to do 2 of them today. I hope we'll manage to do 2 today, otherwise we'll have some trouble tomorrow. And one of them, the first approach, will be by hand, starting with n equals 1. So, as I've already told you, the n equals 1 content of an n equals 2 vector multiplet is an n equals 1 vector multiplet plus an n equals 1 chiral multiplet. Now, I'm going to have to assume that you're familiar with the basics of n equals 1 Lagrangians. All we're doing when we construct it by hand will be to construct it starting with our knowledge of n equals 1. So what we're going to do is to write down the simplest n equals 1 action for these fields and claim that it actually has n equals 2. So the n equals 1 action for the vector multiplet, well, it can be written in nicely in superspace. I won't explain what that means, and I will just reduce it to a description by ordinary fields. There's the kinetic energy for the gauge field. There's the kinetic energy for the fermion, but only lambda 1, the one that's in an n equals 1 multiplied with A. And then there's an auxiliary field, which is usually called D. If you ask what representation of the gauge group D is in, the answer is it's in a supermultiplet that contains the gauge field, so it's in the same representation as the gauge field, namely the adjoint representation. Then the rest of the action, I'll give a name, capital Phi, to our chiral multiplet. So remember, chiral multiplets exist in any representation of the gauge group, but here we need the adjoint representation because this is supposed to be in an n equals 2 multiplet with the gauge field. It has to be therefore in the adjoint representation. So its action in superspace looks like so, but in ordinary language, okay. Although usually it would not be natural for chiral multiplets to put a 1 over e squared in front of the action, here we will. We rescale phi to enable us to put that term there because we want it to have a symmetry with the gauge fields. So now there is a kinetic energy for phi. And there's a kinetic energy for the second fermion. And there's a coupling of the auxiliary field to a bilinear in the scalars. And then there are some Yukawa couplings that we should worry about. The Yukawa couplings, well, the whole Lagrangian is bilinear in the chiral superfield. So a Yukawa coupling will involve a phi with a lambda bar 2, and it will it'll multiply a gauge field, a fermion that comes from the vector multiplet. That'll be a lambda bar 1. There's also, it's possible. Yes?
What did you say the theta angle to 0 in the gauge?
I set it to 0 because we'll talk about it later on. Okay. If there is an n equals 2 Lagrangian, we can add a theta angle without spoiling n equals 2. Because since the theta term is a topological invariant, it's invariant under arbitrary infinitesimal deformations, including supersymmetric variations. So since the theta term is supersymmetric by itself, it's not the problem. The problem is to write the rest of the theory. It's customary to put an e to the v there. Okay. Well, anyway, let's accept it. So the other Yukawa coupling would involve phi bar times lambda 2, and then it would multiply lambda 1. So I'm writing lambda 1 or lambda I. These bars are, I'm afraid, of what I've usually called alphas. Lambda is a fermion of one kind, one helicity, or one chirality is a better term off shell. And lambda bar is a fermion of the opposite chirality. So where there's a lambda bar 2, we'll have to multiply a lambda bar 1, or we can't make a Lorentz invariant. And likewise, where there's a lambda 2, it would have to multiply a lambda 1. But Lorentz invariance alone doesn't tell us whether what multiplies lambda bar 2 is phi or phi bar. Although Lorentz invariance doesn't tell that, the internal symmetries do. So let's look at the global symmetries. By global symmetries, I mean Lorentz invariant bosonic symmetries. There's an obvious U1 times U1. one U1 acts as phi going to e to the I alpha phi. And we could write phi as a bosonic field plus theta times lambda plus stuff. So phi bar will be the complex conjugate of phi bar plus theta bar times lambda bar plus stuff. And you see that phi and lambda both have charge 1 under this symmetry. It doesn't act at all on the vector multiplet. So it tells us that I've written this correctly. Phi has to go with lambda 2 bar, and phi bar has to go with lambda 2. Lorentz invariance then fills out the rest of the structure. Of course, there are numbers in these formulas. You find the right numbers by doing the theta integrals. So that U1 symmetry actually determines the form of the Yukawa couplings, but I want to go on and point out that there's also an R symmetry. The R symmetry acts on superspace by x going to x, theta going to e to the I beta, let's say, times theta, and theta bar goes to e to the minus I beta times theta bar. That didn't work. Assuming I want you to be able to see what I just wrote. So we use the more trivial symmetry under which the whole chiral multiplet transformed the same way. But there's a slightly less trivial R symmetry where theta transforms. So you see, by possibly combining it with the first symmetry, I can define it so that phi is invariant. And then if theta picks up in e to the I beta, we see that lambda 2 picks up in e to the minus I beta. This is under the U1 R symmetry. And to make the Lagrangian invariant, you can see that lambda 1 transforms oppositely to lambda. So the two symmetries we know about are indeed realized by this Lagrangian. But for no added price, we get more. The reason we get more for no added price is the following. Well, just look at the Yukawa couplings again. It's enough to look at this term because this term is at the Hermitian adjoint and therefore has the same symmetries. So this term we can write more invariantly as epsilon ij, epsilon alpha beta, lambda alpha I times lambda beta j times phi bar with a trace of all that mess. You see, it was already anti-symmetric in the alphas in the Lorentz indices for Lorentz invariance. It's also anti-symmetric in, I should have made this clearer. It's anti-symmetric in the gauge indices because this coupling came from the gauge transformations, gauge couplings of the adjoint representation. So everything you can, the couplings of the gluon to itself involve commutators of generators of the Lie algebra. And when you extend it by supersymmetry, you just get more commutators. So just like the gauge field in the covariant derivative couples to phi by a commutator in the Lie algebra, the same is true for lambda 1, which is the superpartner of the gauge field. So this coupling is a commutator in the Lie algebra, which is anti-symmetric. So it's anti-symmetric in Lorentz indices, anti-symmetric in gauge indices, so therefore it's automatically anti-symmetric in the internal index, which takes values 1 and 2 because there's n equals 2 supersymmetry. So I've written it in a way that makes manifest all the symmetries by writing it with an antisymmetric tensor. See, epsilon ij takes non-zero values 1 and 2, or 2 and 1, but they make equal contributions and give that expression. So for no added cost, the Lagrangian has extra symmetry by accident. It has an SU2 symmetry that acts only on fermions. Lambda 1, lambda 2 goes to m times lambda 1, lambda 2. Well, if the determinant of m is 1, we get a symmetry that only acts on fermions. But we actually can relax the assumption that the determinant of m is 1. If we transform phi to the determinant of m times phi, where m takes values in U2. So since m is in U2, its determinant is in U1. Its determinant is of absolute value 1. And here, lambda lambda will transform like the determinant of m, and then phi bar will transform like the determinant of m inverse, the complex conjugate of the determinant of m. So we actually have a U2 global symmetry. The U1 times U1, which is obvious, of course, is embedded in U2 as the diagonal matrices. So in other words, the realization by n equals 1 supersymmetry enabled us to see the diagonal part of U2. Now, this U2 symmetry doesn't commute with n equals 1 supersymmetry. After all, the n equals 1 algebra was that delta A mu was epsilon bar gamma mu lambda 1 and more stuff. But now we've got a U2 symmetry that doesn't leave lambda 1 alone. It mixes it with lambda 2. So there's the same Lagrangian, therefore, has a completely equivalent symmetry with lambda 1 replaced by lambda 2. And that promotes the n equals 1 supersymmetry to n equals 2 supersymmetry. So the n equals 2 generalization is that delta A mu is epsilon bar I times gamma mu lambda I, summed for I equals 1 and 2. That's just the supersymmetry transformation for the gauge field, but of course we have to add corresponding transformation laws for all the other fields. So, any questions about this? So we've made our, yes?
Does this Lagrangian has some symmetry?
Yes, it's a gauge invariant Lagrangian.
For
Whatever gauge group we started with is the gauge group we've got. The construction was for any compact gauge group, and the only reason we want it to be compact has nothing to do with supersymmetry, otherwise the energy isn't positive. I did assume you were familiar with the n equals 1 gauge theory construction. That involved any gauge group. We simply imitated it for n equals 2 and found that we got n equals 2 for free, given n equals 1. Any other questions? Now we're going to say the most trivial thing about the dynamics of the theory, which we'll only look at classically for today. So we want to find the potential energy of the theory, which we find by integrating out the auxiliary field D. So the equation of motion for D relates D to the commutator of phi and phi bar. And after we eliminate D, the potential energy becomes E squared times the trace of the commutator of phi and phi bar squared. The I there makes the commutator Hermitian, so that the trace is positive. So V is 0, it follows, if and only if phi commutes with its adjoint. Now, any matrix commutes with itself, but most matrices would not commute with their adjoint. It's equivalent to saying that the Hermitian and anti-Hermitian parts of phi commute with each other. And since they commute with each other, they can be simultaneously diagonalized by an SU2 gauge, by a gauge transformation, whatever the gauge group is. We'll take SU2 for an example, though. So phi commuting with phi bar means that we can diagonalize phi by an SU2 transformation. So for zero energy, phi is a diagonal matrix with some arbitrary eigenvalue A. A is any complex number. But A is not quite gauge invariant, because we could make a gauge transformation that would exchange the two eigenvalues of phi. What's gauge invariant is not A, but the trace of phi squared, which is 2A squared. Or I think, which we'll call U. So U is a complex parameter that describes that labels the possible quantum vacua of the theory. Sorry. To begin with, it labels the possible classical vacua. But after quantum corrections, it's also true that U parameterizes the possible quantum vacua. And our goal will be to understand the properties of the quantum vacua that are parameterized by U. So it takes some work to do that quantum mechanically, but classically we kind of get the answer for free. So what I'm drawing now is the complex U plane. Now obviously there's an exceptional case where U is 0. U being 0 means that phi is 0, so the SU2 gauge symmetry is unbroken. But when U isn't 0, SU2 is broken to U1. Now, we understand U1 gauge theories, or at least we think we understand them. As far as we know, U1 just produces Coulomb forces. But SU2 produces strong gauge dynamics, which in the case of the nuclear force, there the group is SU3 rather than SU2, but the basic idea is the same. Strong gauge dynamics is very difficult to understand. So it'll turn out, because of asymptotic freedom, that for large U, the classical picture is valid, but when we move into U equals 0, we have a simplified analog of the problem of strong interactions, understanding what happens when the gauge dynamics become strong. So the problem we'll try to solve of how the quantum theory behaves for small u is a kind of simplified cousin of trying to understand the strong interactions. Okay. Okay. So, let's look at the spectrum. For u not equal 0. Well, the massless states are the same theory for U1. At low energies, SU2 is broken to U1. The massless states are just the U1 gauge field and its superpartners. And you know what the spectrum is? We have a massless vector multiplet. We constructed this theory to have for any G the fields corresponding to a massless vector multiplet. So the SU2 gauge fields had an accident and some of them got massive, but the U1 part is unchanged from what it was classically, and we have massless U1 fields, yes?
So phi is in the adjoint of SU2, right?
Yes?
So that shouldn't that break SU2 to 2 U1s and not
No.
just
SU2 is the group generated by 2 by 2 traceless Hermitian matrices. If we were in U2 with no restriction on the trace, the unbroken group would have consisted of 2 U1s. But because the group is SU2 and the generators are traceless, the only traceless matrix that commutes with that is a multiple of itself. There's only a single unbroken U1. Any other questions? Okay. I'm going to have to ask the organizers to let me use what was supposed to be the question time, since we are asking questions. When am I supposed to finish, Nima? Well, I don't want to keep going indefinitely. Okay. Okay. So for U1, so we have the massless vector multiplet, which by now we know has 8 states. It's this 1, 2, 1 doubled. But now let's look at W bosons. For example, W plus bosons. Which correspond to strictly upper triangular matrices. Well, they're massive. That's what the Higgs mechanism does for us. On the other hand, the representation didn't get bigger just because they were massive. The number of fields is not changed when we gave phi a VEV, and the W boson states that come by quantizing the fields don't change in number, they just get mass. So there are still 8 states, just as if U were 0. So the spectrum is the same thing. But they're massive. Now, we know that if we're going to have a massive multiplet with only 8 helicity states, there has to be a central charge. So there is a central charge. And so when I recommended preliminary reading, I recommended the first of my 2 papers with Seiberg, but I probably should have also recommended a paper I wrote with David Olive. So in that paper, we calculated the anticombinator of two Qs in this theory. And naively at 0, because there's no obvious bosonic quantity that could appear in the supersymmetry algebra. But when we actually calculated it, we found that there's a surface term that previously had been, in fact, overlooked. So F0I plus is a half of the electric field plus I times the magnetic field. So F0I plus regarded as a vector is the I component of the electric field plus I times the magnetic field. So this expression, of course, since it's the integral of a total derivative, you can write it as a surface term at infinity. But what are those surface terms? Well, the electric field at infinity measures the electric charge, and the magnetic field at infinity measures the magnetic charge. So in fact, this expression is A times the electric charge plus I over E squared times the magnetic charge. If you wonder why one of the terms has a 1 over E squared and the other doesn't, it's because with our normalization of a 1 over E squared in front of the Lagrangian, the electric field due to a unit charge is proportional to E squared. So that cancels the 1 over E squared. I'm defining the electric and magnetic charges so that they are integers, roughly speaking. I'm not going to attempt to get all the factors of 2 right in front of your eyes. But we are getting the factors of E squared right. So the E squared goes away for the electric charge. Because the electric field of a unit charge is proportional to E squared. But there's no mechanism to get rid of the 1 over E squared in the magnetic charge. It just stays there. So what Olive and I calculated, and we calculated this by just using Poisson brackets. We wrote down the standard formulas for the two Qs and computed their Poisson brackets. What we computed was that classically the central charge is A times the electric charge plus I over E squared times the magnetic charge. So therefore, the mass of any particle is equal to or bigger than the absolute value of Z, which is the absolute value of A times the square root of Q electric squared plus Q magnetic over E squared squared. Now, our little discussion was for W bosons, which have no magnetic charge, but they have, we'll be more careful about the units tomorrow, but loosely speaking, they have unit electric charge. So for W bosons, the formula says that the mass is equal to or bigger than the absolute value of A. Oh, sorry. That's what the inequality says. But for small representations, the inequality has got to become an equality. I think I forgot to say that small representations are also called BPS representations. The inequality becomes an equality. The mass is the absolute value of A times the square root of Q electric squared plus Q magnetic squared over E squared, squared. So for W bosons, given that they are in a small representation, the mass is simply the absolute value of A times the electric charge. And that's the Higgs formula. In other words, the standard Higgs formula is that the W boson mass is the absolute value of the Higgs field, which is here the absolute value of A.
So what is A?
What is A? A was introduced earlier by saying that the vacuum expectation value of phi was a matrix whose eigenvalues were A and minus A. Any other questions? Yes?
What do we get on the right-hand side for the unbroken theory?
We get on the right-hand side 0. And that's the right answer because in the unbroken theory, the W boson is massless. Any other questions? Now, we'll come back to this formula tomorrow when I might have to talk a little bit faster than I'm talking today. But I do want to point out why this factor of I was important. The factor of I in the central charge, which was there because, you see, Q was chiral, and in the computation I did with Olive, that leads to what appears here being also chiral, which for gauge fields means it was self-dual. But self-duality in Lorentz signature means that the gauge field is complex. The self-dual combination is the electric field plus I times the magnetic field. So it comes about in that way that there's a factor of I in the central charge. And it happens then that when we take the absolute value of the central charge, there's no, we get 0 times Q electric times Q magnetic. That's a happy state of affairs because the cross term would have been odd under CP. Under CP, electric and magnetic charges transform oppositely. Actually, the C has nothing to do with it. It's more P that does that. So anyway, because of CP symmetry, that's why that term came out to be 0. Now, of course, one of the previous questions pointed out, and this also shows I'm wrong. I made an incorrect statement a moment ago. We could have violated CP by turning on a theta angle. And the answer I gave at that time was that we weren't going to worry about it because trivially we could add the theta angle without spoiling supersymmetry. But when we do add the theta angle, it violates CP, and the formula will change a little bit. The cross term will not be 0 anymore, which will be possible because the theta angle has broken the symmetry. Well, we'll come back to that tomorrow. But I really want to do today is to squeeze in a second way to describe the theory. I wonder if it's practical. We'll try. Depends on how fast we talk and whether the organizers let me get away with it. So, I promised 3 constructions of the theory. I'm going to have to zoom through the second one. The second one is we're going to do minimal super Yang-Mills in d dimensions. The only fields are gauge field A mu and also lambda, which is a fermion. And we'll take only one. We'll take the smallest possible fermion. But what that means depends on the dimension. We're going to do this in d dimensions. In some dimensions, lambda can be Myron of Isle. In other dimensions, it can't be. But whatever the dimension is, we'll take the fermion of the smallest possible dimension that's allowed by Lorentz invariance. And then we write down a Lagrangian, which is just the minimal one. Now, we will give ourselves the benefit of the doubt and let lambda be in the adjoint representation. Otherwise, supersymmetry is hopeless. And now we simply will ask whether the minimal Lagrangian is supersymmetric. Now, if it is supersymmetric, the gauge field variation on dimensional grounds has to be given by the usual formula. I think I'll use capital gamma for my gamma matrices in n dimensions. And gamma mu nu, just as in 4 dimensions, is the anti-symmetric part of the product of gamma mu and gamma nu. And then you ask whether this thing is supersymmetric. And a small but very pretty computation shows that the term linear in lambda cancels in any dimension. So let's see. If I vary the gauge field, I could vary either of these two f's, giving a factor of 2. And then I get another factor of 2 because I have to vary d mu of a nu and d nu of a mu. So we get d mu of then if I vary lambda, I can vary either of the two lambdas. So that gives a 2, but it will be half times that 4 outside. Now, you use a little bit of gamma matrix algebra, and you integrate by parts. And magically, this turns out to be 0. So we have to use the following fact. Gamma mu, gamma alpha beta has an anti-symmetric part, and it also has a symmetric part. The reason I'm going to the trouble to write out this stuff on the blackboard in front of you is that if you actually want to work on supersymmetric field theory, you've got to be familiar with this kind of computation. I think if I just say that, you won't believe me. So to make you believe me more, I'm doing at least some of it in front of you. So we get to complete the anti-symmetric part, which magically is 0 because of the Bianchi identity. Then we get a part with only one gamma matrix, just like this one. And if we integrate it by parts, the derivative will act on lambda just as it does here. And after you're a little bit more careful with factors of 2 than I will be right now, given the hour, you find that those two cancel. I didn't quite demonstrate the cancellation, but from what I've said, it's almost obvious that it cancels if we get the right power of 2 here. Because it's got the same structure. There's an F, a single gamma matrix, and a lambda, and one derivative. And there's only one Lorentz invariant way to put that stuff together. So in any dimension, the part linear in lambda cancels. But there's actually a part which is cubic in lambda, because we could take the gauge field inside A and vary that. So we have lambda bar times gamma mu times A mu commuted with lambda, and we vary it with respect to A. Well, that's a loose notation. We take delta A to be this thing. And you see, we'll get something which is cubic in lambda. We get something that can be written like so. It came from gauge theory. So in gauge space, implicit is a commutator in the Lie algebra, which means it's completely antisymmetric in the gauge theory indices. It's got to be 0, and nothing's going to help it to be 0 except Fermi statistics. So since it was completely antisymmetric in gauge theory, it's going to be completely symmetric in the spinor indices. So the only hope is that gamma mu alpha beta times gamma mu gamma delta plus 2 more terms to make it symmetric in alpha beta and gamma has to be 0. That's a wonderful identity. That's true in and only in d equals 3, 4, 6, and 10. So the 4-dimensional case is n equals 1 superiomials in 4 dimensions, which I assumed you knew about in the first construction of the theory we wanted. But for today, we want the 6-dimensional case. Now, I've planned in my notes to prove this identity in 6 dimensions. I don't know, though, if I should, given the time. I'll try to tie up the loose ends, assuming that we knew about that identity. We then have a d equals 6 Lagrangian, which is supersymmetric. But I told you what we were going to get was a second construction of n equals 2 superiomials in 4 dimensions. How do we get that second construction? Starting from 6 dimensions, well, we just brutally take the fields independent of the last 2 dimensions. So we write our fields as time and x1, x2, x3. We think of that as Minkowski spacetime. But then there's x4 and x5. We drop the dependence on these. So we let phi be a4 plus I a5. That's a complex scalar in the adjoint representation. And then we have also a gauge field, a mu, where mu runs from 0 to 3. And then lambda becomes 2 spinors in d equals 4. The way that happens is that an irreducible spinor in d equals 6 has twice as many components as an irreducible spinor in d equals 4. So the Lagrangian, this minimal 6-dimensional Lagrangian, when we drop the dependence of the fields on 2 coordinates, and write it out in a four-dimensional notation is exactly the same Lagrangian we had before. So that is our second construction of n equals 2 superangles in 4 dimensions. And by the way, if we were aiming for n equals 4 in 4 dimensions, we would do the same starting from 10 dimensions. Now, one reason I gave you the second construction, well, first of all, you should certainly know about it if you want to work on supersymmetry, but it gives a new explanation of why there are central charges in the supersymmetry algebra. The 6-dimensional theory looked like so. And of course, Lorentz transformations, although I haven't written them on the blackboard, act by outer automorphisms of this algebra. They act on both Q and P. But from a 4-dimensional point of view, we write this as what should be there on the right-hand side in 4-dimensional supersymmetry, but there are 2 more terms. And, well, what are the 2 more terms? Well, the momentum commutes with the momentum and also with the supercharges. And they commute with 4-dimensional Lorentz transformations, which are all that we've got left when we drop the dependence on 2 coordinates. So these 2 terms become central charges. In fact, they become electric charges. In the same situation we were discussing before, with SU2 broken to U1, the right-hand side becomes the part of the central charge that arises from electric charges. You have to be a little bit more careful to see the magnetic charges, and I think there isn't time for it today. Now, I'm going to have to stop because there are more things going on later this afternoon. As tempting as it would be to just keep going and try to catch up with where I was supposed to be in this lecture. And so we'll call it a day. Yes?
So if you take the hypermultiplet on the half of it, let's say on the S representation for 2.
Speak louder, sorry.
If you take the half of the hypermultiplet, like 1, 2, and 1, and try to build up a Lagrangian, what kind of discrete symmetries is it going to have?
It's not going to work.
So not CPT, but...
Well, the CPT theorem is a theorem. It's not just good advice. What the CPT theorem says is that all Lagrangians are CPT symmetric, among other things. The CPT theorem is stronger than a statement about Lagrangians, but it's really a statement about CPT can't be spontaneously broken. It's a statement about quantum theories, not just classical theories, but in particular it's true classically. So using the classical limit of the CPT theorem, you won't be able to write this Lagrangian. Try. Yes?
So if you try and do something like high temperature restoration of your SU2 symmetry, would that work? Because I believe you need Z equals 0 for...
Well, we analyzed what were the possible vacuum states at 0 temperature, and they were completely degenerate and supersymmetric for all U. But at positive temperature, supersymmetry is lost, and that degeneracy will also be lifted. So it's not the direction we'll be going in, but it's certainly true. The temperature breaks supersymmetry and spoils that degeneracy. Any other questions? Yes?
What is the third construction?
I will, I believe, sneak in the 3rd construction tomorrow, but I'm going to have to consult with John Bagger about whether he's doing it, because since I'm behind, I will have to cut out some things. But the 3rd construction was supposed to be superspace. There's a very elegant superspace construction of the n equals 2 vector multiplet. It's hard for me to leave it out completely. It was supposed to be part of the input for the way we were going to do Seiberg-Witten theory. So if I leave it out completely, there will be there will be gaps in my explanation. Any other questions? Yes?
Is it possible to obtain these restrictions on the dimensions for the minimal supersymmetric gauge theory just by counting degrees of freedom in the representations? Or do I need
Yes, it actually, necessary conditions. But the fact that
Sufficient.
well, you can prove that it won't work in the wrong dimensions. What has been suggested here is the following. If you count the number of fermion helicity states in our Lagrangian here, the number of boson helicity states is d minus 2. And the number of fermion helicity states is generically not equal to d minus 2. So in most dimensions, it can't work. If you use that criterion, you'll find that the candidates where it might work are d equals 3, 4, 6, and 10. But that does not show that it does work in those dimensions. There's a wonderful group theory identity which magically works in those dimensions. And I intended to demonstrate it in front of your eyes for d equals 6. It's somewhat analogous to the existence of exceptional Lie groups. So there's a little bit of magic that goes into the fact that it works in those dimensions. If you thought it was a sufficient as well as necessary condition, that was a little misleading, I would say. Yes?
If the gauge group G breaks to H and both are non-abelian,
Yes?
then the central charges, do they have some notion?
Well, do they have what?
This notion of electric and magnetic.
Well, let's just discuss this on the basis of our knowledge of physics. So, okay. Non-abelian gauge theory in 4 dimensions tends to be strongly coupled. So you tend not to be able to put particles in representations of SU2 or SU3. It gets confined if it's unbroken.